All right. So I think we get now to the real fun part of this. This is going to be now a presentation that I'm going to do on COVID. So let me share my screen with you all and start the presentation. Just give me a little bit of feedback if you can. Can you see my screen?
Yes.
Yes. Okay. Excellent. Excellent. So this is of course a view from Switzerland, where I live and strive. And this is not the view from my window, but this morning as I went to work, well, this was the view to my office. And I know that Andreas Gartma has joined us, and he probably knows where because his office is very next to mine, he knows where I took that picture with some of the mountains. Those who know the Swiss mountains well, they are far there between the two bigger mountains. Far in the end, you could recognize the Eiger. So fantastic view, just a minute away from our offices. Andreas is in mine.
That's right. That's right. But you're closer. I don't have such a nice view.
All right. Okay. All right. So just again, let me remind you a few things about this video conference. This is we're getting more and more used to having those conferences online. We know that it's being recorded, so behave. Also, and this is pretty good, all of you, as far as I can see, have indicated your name. Sometimes there are some numbers, or it's just nice to know the name of the people. If you have a camera, please don't hesitate to turn on the video and also the sound. If there's no background noise, then just turn on the sound, and so you can intervene at any time. Let's try to make it as though we were in the same room. If there is background noise, yes, then mute. But if you want to ask any question, please interrupt anytime, as you would do it in a room where we would be together. Don't try to raise your hand or whatever. Just interrupt and say, Frank, I have a question. Or Saraya, Jeff, Kendra, I have a question. Okay, the breakout room, well, we already went through this, is for the quizzes. The chat box, if you want to communicate with us, don't necessarily do it with a chat box. If you can, just do it by unmuting, if you're muted, and just speak out loud and interrupt us. The thing is that the chat box, I mean, I'm not going to read that chat box that regularly. And if you ask a question there, you might get your answer only after 10 minutes or worse. But where you can use the chat box is you get the questions are listed in the chat box, and also the slides. This slide here, for those who joined earlier, you already had the download of these. I uploaded the slides and also the calculation templates, because we're gonna do it in kind of in stereo. We're gonna do PowerPoint and we're gonna do Excel at the same time. We're gonna illustrate the theory that I do in PowerPoint. All right. Okay. A few, not meeting, but meeting stats. All right. Well, this is how you guys registered. Obviously, every time there's an announcement, people wake up. Oh, yes, I should register. That's interesting. But the really interesting is that we are just short of 100 people who registered. Turns out that in the meeting, well, we're only about 50 people. So as usual, people register, but then they don't come. All right. In terms of where people come from, I'm going to be a bit more precise.
Yes to both. The geospatial tools have really matured to where you can really put them to use. Where they really have value, I think, is smoothing out the noise that you'll see when you play with the localized data.
Mike, are you talking to us, or are you talking to someone else? What you need to do with the
geospatial tools is say, look at one.
Okay, I'm going to mute. Mike, I think you're not talking to us, so all right, now he muted. All right, okay. Okay, I was a bit confused because I was just going to talk about geography. Where do people come from? Well, the bulk, most of you are from Switzerland. That's generally like that. The CAE meetings, at least those that take place in Switzerland. But now who are the others? Well, there we are. Well, we have the UK. We have lots of people from Italy. We have, and now people who join us from the US. Hello, good morning. We have people also joining us from Mexico. I mean, 4 people joined us from Mexico. So, I mean, it's never been as international, and I'm really amazed from Australia. I mean, from even here, Peru, and yes, I've seen you guys. I've seen Jose, who was from Mexico, and I've seen Guido, who joined us from Peru, and South Africa. We have also from, I guess, NG. That's Nigeria. Is that correct? Well, so also we have.
Yep.
All right. Okay. Welcome on board. So it's never been as international thanks to Corona. Okay. So let's start. So what I'm going to do is I'm going to talk about some types of models, a really important family, a traditional family of models, the compartmental epidemiological models to model epidemics and pandemics. And then I'm going to concentrate in the second part on one particular of these models, the SIR model. No, it's not a knighted model. No, it just stands for susceptible, infected, and removed, because we have 3 compartments. We get to that. And then I'll say a few things about that model, which is really quite interesting, although it looks simple, but it has a very vast phenomenology. And I'm going to compare the phenomenology of that very simple model to the data so far. Okay, so what am I talking about when I talk about these compartmental models? And let me start with the really simplest. That is the SI model. The SI model, you start with a group of susceptible people. You're not ill, but you could get ill. And then tough luck strikes and you are getting ill. You're infected. And you're infected with a certain rate, alpha, and it's proportional to the number of people who are infected, because they are infecting you. We're talking here of epidemics, so these are infectious diseases. So you get infected by somebody, and the more people are infected, the higher your chance, and also the more people are in that block, also the more there's going to be a flow from this box to that box. But then eventually people just they recover, and they get back from this infected part, they get back then to susceptible. And this now is only proportional to the number of people who are infected. So if you want to write this in equations, before I do that, this is a model with no immunity. And an example would be just the common cold. The common cold is, that's interesting when you prepare a presentation like that, you learn a lot about things you never knew before. It turns out that the common cold is due to viruses, and many viruses. They're talking about about 100 different viruses that have been identified for the common cold. That's why we don't develop immunity to that, because one year you're infected by one, and then afterwards you're infected by another one. But this is the characteristic of successful viruses. Successful viruses don't really bother their hosts too much, let alone they don't kill them. I mean, the viruses who kill them are very unsuccessful viruses for obvious reasons. And luckily, they're very rare. Actually, most viruses and like most bacteria are totally harmless to us. So that's why we don't develop any immunity, because there's so many of those. And it could very well be that in 100 or 200 years from now, also this COVID strain will have developed many, many different subgroups of this COVID-19. And those who will really survive are those that are harmless to us, or just don't bother us very much. And they're going to be also hundreds of them. And we will not develop any immunity any longer, but who cares, because they're just not going to bother us. Okay, so now the equations for this, just writing now in math what I said there before. The susceptibles, they go to the infected here with this rate alpha IS, proportional to the number of susceptible and number of infected. But then from the infected, there's a certain number that becomes susceptible again, and here vice versa for the I box. You notice that these differential equations, if I sum them up, if I add them up, I get here to n being the sum of s and I. Well, this derivative is 0. This is a model where the total number of the population stays constant. So it ignores things which for some types of epidemics is important. It ignores natural death and ignores also birth rates, and it ignores also migration. So for us in COVID, well, we can certainly ignore death and natural death and birth rates, because the time scale of the epidemic is relatively short. That's different though for something like HIV, for instance. Okay, so that is a very, very simple model. It is still quite nice because if you look at these equations, they're quite, they might be reminiscent to you if you've ever seen the Volterra equations, which are also, which actually consider the populations of foxes and rabbits or sharks and herrings. Well, if there are many sharks, they're going to eat all the rabbits, no, the herrings, and then as there are less herrings, well, then the shark population is going to decrease and the herrings are going to start. So these are fluctuating, they are periodic solutions. Very nice equations. So these are of the same kind here. Okay, but let's go one step further. The SIR model. Now we start with the same way here, susceptible to infected, but we have now a next box, a next compartment, and that is the compartment which is going to take into account that we can develop immunity. We have only one or very few strains of viruses, and if you have developed this immunity, you're removed from the pool. Now note, removed, it could also mean that you just died, you're gone. So this model doesn't make a difference whether you're just healthy again or whether it really went the opposite way and you're dead. You're just removed from the pool. Okay, so it doesn't make that difference. We're going to get to that in a few minutes. So now when we do that, the equations, there's a third differential equation, the equation that corresponds to this pool here of removed, and it's simply this beta I just goes now to there. Remember with the previous one with the SI model, the beta I we just went in this direction here. All right, so it only goes in one direction. It looks simple, it's already quite rich, and we're going to see that. And that is the standard model of epidemiology. Now, all the others are kind of getting a little bit more complex, adding more compartments, but already that one with only 2 parameters is already describing a lot, and I will convince you, I hope I will convince you in the third session that I'm going to do about this. All right, so this one applies to the flu and COVID and many other diseases. And again, we have this conservation law here where with the total number of the population. Now, you can also, I told you, well, here people, they're removed, they could be just healthy again, or they could have died. Well, if you want to include that subtlety, well, you can do the SIRD model. Well, the D then obviously corresponds then to deceased. And so you add a 4th compartment here, and it's simply same dynamics here, but with a different rate here, with hopefully the gamma being small. Now that could be interesting here in our modeling of the COVID epidemic, because, well, people die, and that is something which is relatively easy to measure. If somebody's dead, well, he's dead. He's not half dead. Huh? You could be half recovered, but dead, you're only fully dead. It's like pregnant. You're not half pregnant, or you're not extra virgin. Okay, so for measurement, for calibration purposes, that could be useful, although then be mindful, because it turns out that in some countries, you wouldn't believe this, they counted the COVID deaths only as those who died in the hospital and not those who died at home. So that completely distorted statistics. So one of the main challenges here in modeling the epidemics is understanding what the data means, and also what it means over time, because of course the way they record the data changes over time. Again, we always have this conservation law in those models. There are other models, and you could also, in principle, you could also apply that to COVID. It's models with an incubation period, like for example rabies, which has an incubation period of 1 month approximately. Yeah, Wikipedia is so good. I mean, you learn so much on Wikipedia. I mean, a few weeks ago, I would never have known that the incubation period of rabies is 1 month. And then, well, here you add in between, between the infectious and the infected, the infected you divide it in two parts, the exposed and the infectious. And that corresponds here to the immunization, the incubation period. All right. You know, this is so good because I have one screen where I see this presentation. I have this other screen where I can see you, and I see that one of you is on mute and he's calling there on the phone. He's not concentrating on what I'm saying. This is so good. I can really check you out. All right. Then you could have also models like tuberculosis, which is strangely enough, some people are really removed, they're totally cured, and nothing happens to them any longer. And others are just a carrier, and then they're kind of a ticking time bomb. They can still get into the infected part. This disease can start up again, and they can get back into this pool here. So that's but you see, all these equations, they're always of the same flows that are modeled there with these differential equations. So you see the richness of this, and what I will do is I'm going to stop now in a minute or two and let Jeff start the second round of questions. But just giving you the gist of what's going to come next, so you stay on, hopefully. I'm going to concentrate on this model here, the SIR model. By the way, this is a model which was designed almost 100 years ago. I think it was something in the 30s, in the 1930s, that it was first designed. And why is it still so popular? Because it is as simple as possible, but not beyond. That's why. So it just satisfies that criterion already. Although it's that simple, it already explains a lot. And in the third part of this presentation, I'm going to show you that and compare what the richness of the results from this very simple model with the data. I uploaded on the chat box, I uploaded the slides, but also the Excel files, and we're going to do some Excel files at the end of this, so some Excel examples at the end of this this little session here. Now it turns out that some people told me as a feedback that they didn't manage to open the previous one. It was an XLSM macro-enabled one. Well, I by default always make them macro-enabled, but there's no macro in it. In case you could not open it for whatever reason, I uploaded now another one which is not macro-enabled, and I've been told that one was those who had problems before managed to open it. Okay, so that's where we stopped, and now I wanted to say a few more things about this very simple model, the SIR model, susceptible, infected, removed. And well, this model actually has an analytic or a quasi-analytic solution. Now, how to get the solution of these three equations? The trick is the following. We're going to define a new time here. I'm going to call it tau, and tau is going to be I. Well, that's the number of infected people. Multiplied d tau is I multiplied by dt. So that's my definition of this new time. It's going to be tau. It's going to be a fictitious time, or maybe a natural epidemic or a pandemic time, the natural time of the pandemic, and not our time of usual space time. Okay, when I do this, it turns out that the equations simplify quite a bit, because now this equation here becomes ds over d tau is equal to minus alpha s. Well, that one we know. I mean, even in high school, we knew how to solve that. It's simply an exponential. All right. We've heard exponential growth and so on. Well, here it is. That's where it starts popping up. So we have our initial, at time 0, initial number of susceptibles, and then the number of susceptibles decreases in this time in terms of this time measure exponentially towards 0. Okay, now let's look at the next equation, a simple equation here. Well, it's even simpler. dr over d tau is equal to beta. It's a constant. Well, I mean, I almost could do that in elementary school. It's just a linear equation with, again, this boundary condition. All right. Now, how about this one? Well, this one, I'm not even going to bother about trying to solve that one because I have that relationship. I know it's constant. So what I have, I'm going to set the total number of people. I'm going to set it equal to 1. So it's going to be just relative numbers. I'm going to scale everything to relative numbers. And then I have the relationship I is equal to 1 minus s minus r. But s and r, I already have them. Bingo, I've solved my problem. And here I can show you how it looks like in terms of this time tau. Well, here is my exponential for s. Here is my, well, the sum of the two. Well, first, let's look at that one, the red one. Well, that is this linear function here. And the 1 minus the sum of the two, it's the green one, that's my I. And that's it. I've solved my problem. Except that here I live in a time which is not my physical time, my biological time. It is the time of the pandemic. So I'm going to have to go back now, translate this into real time. And what I do is I integrate this. So t is equal to d tau over I, but I already have it here. So it is an integral of that kind. Now, there was a time when I was good at solving these. Solving integrals. Those times are gone, but I really tried very hard and I used some software, but it turns out apparently there is no closed form solution for that. So this you have to do numerically. But look, I mean, just computing an integral numerically, that is really no big feat. It's much simpler than solving differential equations numerically. So when you do that, you see here, that is the real time as a function of this fictional time. And you see both tiles start at 0 here, and then it looks quite linear here, but it's just here at the end that here you have this asymptote or this pole there. And so if I translate this graph here and I replace this fictitious time, this pandemic time by the real time, well, that's what it looks like. My S now becomes this way. My I becomes this way. Oh, it looks like a wave. And here is my number of removed. And always the sum of all these three curves, these three colors, is always equal to 1 to 100% by construction here. All right. So that is the analytic solution. I don't know how useful it is. I mean, probably it's totally useless. Still, it's so neat. I really wanted to show it to you. And now the way how people solve that in practice, it's doing it numerically, brute force from the start, which is really not difficult either. So how do we do that? We get back to this here and we just make difference equations. That's all. So we have here our ds is s at time t plus delta tau minus s at time t is equal to minus alpha I and s at the time t multiplied by delta tau or delta t.
Yeah. Frank, can I ask a question? Can I, yeah, in the graphs, the proportions that you have are proportions of n?
That's right, yes, exactly. So we say, I set n equal to 1.
Okay, okay.
So if you know that in a country you have 5 million inhabitants, well, you just multiply by 5 million, you have the number of people.
And then the x-axis is time. Why do you have 0 to 200 in the first one and 0 to 20 in the second one?
Because this is the time tau. And the time tau actually only goes up to something like 18 in that case for those parameters.
Okay,
Doesn't go beyond. It never goes beyond that.
Thank you.
But when you translate here, you see that this time here is limited, whereas the real time is unlimited. That's why you have this asymptote at that pole here. So this one goes then to 200. Yeah. Okay. And in this case, I've tuned the parameters alpha and beta in such a way that we have something like 50 days here, 100 days there, and so on. And I'll show you how I can tune that, how I can get the timescales working. Actually, it's just that if you look at the dimensions, I mean, this is a good question. I mean, lots of things that pop out of that question. If you look at the dimensions of alpha and beta, you see that alpha and beta have the dimensions of 1 over time. So actually, 1 over alpha and 1 over beta gives us a time scale. And we'll get to the interpretation of those time scales. All right, so here's my difference equation for S. Similar here for I. It's just the same procedure. I mean, this is something we've done at first year university, and then we still have that relationship for the boundary conditions. So now I use this relationship only for the boundary conditions. I say at time 0, the sum of them should be equal to 1. All right. And when I do that miracle, I get exactly the same graph as before. So up to small rounding errors, this is the same graph as that one here with the analytic solution. Well, luckily.
Frank?
Yes. Yes, Carsten.
Any practical information about step width that is useful? Or is it just try and error because it's so fast and so easy that you can just try and...
It's so fast and so easy, just take a small one. Take a small time step. I think I took a time step. I think I took a time step of a fifth of a day, of 0.2.
Okay, thanks.
Another thing that you can do is, I mean, just to look at this here, the same graph here, but put it here in a logarithmic scale. Well, why do you want to do that? Well, it's because here, when when you want to look at the tails, what happens there, you don't see it in the linear scale, neither there. And moreover, we're talking about the exponential growth. It's there in every journalist's mouth, exponential growth. What are we talking about? Well, if you put it in the logarithmic scale, the exponential growth is a straight line. And when you just replace this scale here by a logarithmic scale, you see, yes, the number of infected here, the green line, yes, it increases linearly. Of course, up to a certain top. I mean, we know exponential growth is something that's not sustainable. Eventually, it's going to stop. So when we're talking about exponential growth, let's just be clear. The exponential growth is only at the beginning of the pandemic. At the midst of the pandemic, there's no exponential growth any longer. I mean, eventually, it's going to stop. I mean, everybody is going to have been affected, or everybody has died out, and then it's over. But at the beginning, yes, we have that exponential growth. All right. So some basic facts about that. The number of results that you can find out with that. And it's what you've heard there in the press all the time, the basic reproduction ratio or basic reproduction number. Well, what you do is you assume you are at the beginning of the pandemic. So we are now in the exponential growth mode. We're at the time almost 0. So then S at 0, this number of susceptible is all 1. The pandemic hasn't started. There are just a few people who are infected now. All right. So now I look at this equation here. This equation at time t equals 0, it's approximately equal to alpha minus beta times I, because S is almost equal to 1. So it simplifies here. It's just this here, but then but that is again something that I can solve easily. In high school, I could solve that. It's simply this exponential growth of I. There we are. So at small times, when S, because S is a number close to 1 and relatively constant to begin, yes, well, then we have this exponential growth here. And we see it will grow, I was saying growth, that is only in the case if alpha is larger than beta. So we will have a growth only if that parameter here is larger than that parameter here. It means that that time scale here is shorter than that time scale. So it's actually alpha, that is kind of the time scale that it takes you to be infected. And beta is a time scale that it takes you to recover. And if so, the time scale of you getting infected is shorter than the time scale of you being recovered, then you have this exponential growth. So you stay infected longer. And that's why we can introduce here this ratio, this basic reproduction ratio, alpha divided by beta. That is the celebrated reproduction ratio that you hear about in the media. Now, the peak that we have here, the peak, well, it's when this here is equal to 0, and that is equal to 0 when S is equal to 1 over R0. And that's no approximation, it's exactly that. And actually, it turns out that here, I did this simulation here with alpha being 3 times larger than beta. So actually I had a R0 of 3, and so S in this case is 1 over R3. You see here my S is at the peak here, it's about at 33%, 1 over 3. All right. Okay, there's something else that you can, I mean, there are lots of things. I mean, I just show you the things that popped to my mind that I thought were interesting. The doubling time. I mean, we're talking about exponential growth. I mean, how long does it take to double the number of people who are infected? Well, you just compute your number of people who are infected at time 2 and at time 1. You assume that you're at the beginning of the pandemic. You're not out here or there. You're here somewhere. You're detecting the pandemic, and if you just do the math, and then you see that the time it takes to double, just to have the number of at time 2 and at time 1, the ratio of them being 2. So the difference of these 2 times is equal to square root, logarithm of 2 divided by alpha minus beta, or for other people, they're going to say it's beta multiplied by R naught minus 1. Again, you see that this only works if alpha is larger than beta. If you manage to reduce your alpha, so basically increase the time that it gets for people to get infected, well, then the pandemic is not going to propagate. There's no doubling time any longer. What I can do is, let me see. Yeah, what I will do now is I'm going to go into the Excel spreadsheet, which you can download from the chat box, and show you how I did that. There we are. So here's our model. I have here all this here. That is the numeric part, and I'm going to go through this. Here's the analytic part. And I'm going to let you go through this, and you can recognize these graphs. I've just taken them in the PowerPoint. I've just taken them from here. and I'll let you just do the analytic part yourselves. The numeric part, well, here again are my equations. Here is my time t, here my delta t, here my s, I, and r. At time 0, I just make sure that s plus I plus r is equal to 1. So I just impose it that way. And I start with a 0 number of recovered and a very small number of infected people. I mean, I have to start with some infected people. If I don't, well, nothing is going to happen. I mean, if I put that equal to 0, you're going to see that, well, nothing happens. That's pretty boring. Okay. Now, I could have started with a smaller number here. It would have been exactly the same picture, just it would have taken a little bit longer for the thing to initialize, but you don't really learn anything. So it's not, I mean, the onset is dependent on that that initial condition here, but not the shape. So if I put here, for example, 0.01, well, the same thing, it just have moved more to the right, and that's it. I can add another 0. Let's see what happens. Well, I've never tried that. Let's see this. Well, it just goes further there, that's all. Not really that interesting. And how do I solve this? Here I compute my delta S, delta I, and delta R. Well, my delta S, I just get it from this equation here. What I do is I take my alpha, I multiply it by S and by I, and I put a minus sign, and I multiply by delta T, and this gives me my delta S. And my S itself is equal to the previous S plus the delta S. And I do the same thing for this one. Here it's a bit more complicated because I have these 2 terms. And here is again simple. I have only 1 term, which is that one here. All right. So I've called this here, I've called it, I've given it a name. It's my SIR alpha. Here is my SIR beta. And here is my SIR not, R naught. SIR R naught, that's what I meant, and it's the ratio of these 2 things. Note that I'm going to play around with this alpha and beta. I kind of don't like them so much because it's has a dimension of inverse time. I can't really think that much. I mean, inverse time, it's a kind of a speed or what, I don't know. It's easier for me to think in terms of times. So actually, I've taken the things that I want to touch is 1 over alpha and 1 over beta. These are the 2 parameters that I'm going to change. So here alpha is 1 over alpha, etc. So, and here you see that the time for people to get infected here is 5 days, whereas the time for people to recover is about 15 days. So, and why have I chosen these? Well, these correspond roughly to what we observed with this pandemic. So we get kind of the same orders of magnitude. And finally, what I plot here, well, I mean, this is I just plot here the my S, my I, my R, and my I. That's it. And I did it here. I did something like 1,000 steps. So Carsten, this kind of maybe answers your question. I just chose to do 1,000 steps, and within in steps of a fifth of a day. Okay. By the way, I should have told you, but actually I did already tell you, but I should have reminded you. If you guys have any question, you unmute and you just scream, all right? Carsten did it. Thank you. Thanks a lot, Carsten. Okay, so I'm going to assume that this was all clear to you, and then when we're going to play again with this, we're going to play with the data, with the real data, and then play also some games with the phenomenology. I'm not going to go through this again. It's the same thing, but we're going to just change the different parameters that we are using, the different 1 over alpha, 1 over beta, and also the initial value of our R of this R here, which is not the R naught, of course. All right. So let me get back now to the slides. We went through this. Now, these are deterministic and continuous differential equations. There is also a stochastic version of that. Kind of makes sense. It's basically a Markov-Poisson process that these models implement. The thing is, going through the trouble of making it stochastic can be useful, but mainly at the begin or at the end of the epidemic. And why is that? That's when you have very few agents involved, very few people. Say you have one person, you have a patient number 0 entering a country and then starting to spread the disease. It's around that time. Once you start having thousands of people infected, there's no real need to use the stochastic version any longer. Because then you're just in the thermodynamic limit. And you can work in a mean field theory, which would be then these differential equations. And there's no difference. I mean, in that regime, there's no difference any longer between the stochastic equations and the deterministic one. So it's only really at the beginning of the epidemic. And there you can see that the epidemic can really die off. I mean, with the deterministic equations, I mean, if I start with this, as I showed you there before in the Excel, with this whatever small value, non-zero value of the infected proportion, well, the epidemic is going to start. But you could very well have in practice having something like 5 people who are infected, and still the epidemic is not going to start.
Yeah, Frank.
Yes,
Frank.
Carlos.
For us non-physicists, what's a thermodynamic limit?
It's the transition from a few body problem, which is quite intractable itself already, to when you start having millions of particles in a gas. Okay, the thermodynamic limit is, I mean, you can describe a gas of a few, like little pellets or marbles, like marbles that are just hitting each other and doing elastic shocks. Yeah. And that's a theory, and you can do this with a few marbles and you increase the number, but once you start increasing the number beyond a certain amount, and this is, I mean, by millions you are certainly there, or in practice the number of Avogadro, something like 10 to the 24 in a mole of matter, well, then you are in this thermodynamic limit. And you can, instead of looking at the interactions, all the different particles, which can be quite intractable, you don't need to do that any longer. You can use a mean field theory.
Okay.
Does that answer your question? Not really. From your expression, facial expression, I didn't answer your question.
Yeah. Yes. All right. Yeah.
Carsten, you may maybe you also have a physicist background.
There's a reason why I swapped professions. I think we just should just take it as a kind of nerd expression and move on.
Okay, it's a nerd expression. It's in the limit of large numbers, all right? Of large numbers of agents. Agents being people like you and me. Any other question? That's the only thing that I'm going to say about data. Can you see it now? That's my citation of Richard Feynman. So you may be as smart as you want. Your model can be as beautiful as can be. Well, if it doesn't agree with the data, it's simply wrong. This is nothing about it. So let's just check that. Let's look at the data, what it looks like. So I'm going to get out of here and into my Excel. Let's look at the data. So what I've looked here is at a number of countries. Actually, by the way, here's a link to a website which one of our participants, Jose Borrego, sent me that was already in July, and it's really updated daily. So here I have actually the update until the 3rd of December. But I'm showing you here the data for Italy up to June, end of June. And so you see here, you see a wave, and let me compare that now to the model. I mean, I've taken that here from our SIR model. Well, you see, well, this looks quite similar. I mean, of course, you have here ups and downs. This could be fluctuations, but some of the up and downs, and we're going to see that very clearly, for example, in Switzerland. There are some days where there are more recordings and others where there are less recordings. In Switzerland, it's quite well. I can't resist showing you Switzerland. Where did I put Switzerland? I put it at the top. Yeah. Well, here you don't see it too well. Okay. Okay. Let me get back. We'll see it later with Switzerland, because in some countries, for example, during the weekend, they do measurements, so they do tests, but they don't well, they take the weekend off. They don't record the test, and they only record it on Monday. So you have, during the weekend, you have a drop in the number of, and then on Monday you have a spike. So, now the thing is, because this is inherently these incremental numbers are always moving around through all places. Well, we know that at the actuaries, it's easier to work with the cumulative numbers. And then you see the cumulative numbers. This is exactly the same information here on the left, on the right as on the left. It's just that here I accumulate all the numbers, the incremental numbers that are observed there. And you see you get a right, nice, smooth curve. And here again, same thing, R being the integral of I. Remember the equation? Well, I can show it to you again. Here the equation. Here's the equation. R is an integral of I. It's the integral of I. So in the data here, in the model here, I show here R is the integral of that. And we see it really follows very much that pattern. So it looks as though this very, very exceedingly simple model actually does a pretty good job of reproducing this data. All right, but here I only went up to beginning of July. And so we thought, well, it was over with, but well, it wasn't. It wasn't because well, simply because we're playing stupid. We're just absolutely dumb. And what happened was the next wave that came, and that one really hit us quite hard. Now, why is it higher? Is it that there are more people infected? Well, maybe. It could also very well be that we now test more people than we used to do before. And here now you see that now here the model in its simplest form doesn't allow for that. Well, the thing is that also the parameters have also changed. And that's why we have that. So let me show you a little bit, because I think this is quite interesting to look at these two curves. So this being the integral of that one. Let's look at this for different countries, and I find that quite instructive. And you see, we go up to for Italy to the second, well, 2 days ago. If I go to Switzerland, I kind of like that one very much. When you look at the data here, well, first of all, you see that what used to be a big peak is a small peak there. Now it's a much bigger one. You see this incredible regularity. Well, that is simply because during the weekend, there's nothing reported, and then on Monday they report what they should have reported in the past 3 days. So that's why you have that. But you see, when you take the integral, it's I mean, these spikes are kind of smoothed out very much here. Interestingly enough, here I'm going to keep the scale moving, but here I'm going to keep the scale to 5%. So if you look at this one here, as soon as you see a rise here, it means that we have a second peak. Let's look at different countries. Let's look at Belgium. I mean, here, this here means that actually 4% of the population has been infected. It doesn't mean that they are still infected. I mean, they might have now they've been removed and not infected any longer. But 4% of the population has gone through this. Let's look now in Belgium. I mean, I'm Swiss and I'm Belgian, so my two pet countries. Belgium is doing better than 4%. No, they're doing worse. Actually, this is one of the worst countries. There's 5% of the population being infected. Now let's look, well, again, with this second peak there. Now let's look in France. I mean, how is France doing? Well, France is doing better than Belgium and better than Switzerland. Germany, they're really good. I mean, they're best in class here. I mean, this is fantastic. I mean, and then look here at this growth that they have here. I mean, this is a linear growth. I mean, this is not, this is pretty good. Italy, it looks bad, but actually, I mean, Franca, this is, I mean, only less than 3% of your population has been infected. I mean, you're doing better than the Belgians and the Swiss. So don't, yeah, Spain here, again, they have the same beautiful, I mean, this is absolutely beautiful. It looks a little bit like one of those dinosaurs I loved when I was a kid. And again, this is the weekend effect. Okay, pretty high, but still better than Switzerland. But Spain is pretty much hit. Okay, let's forget about it. United States, let's look at that one. I mean, up to now, we've always seen there was one peak and there was a second peak, one wave and a second wave. Let's look at the US. Now, the US, this is fascinating. Here is the US. I mean, they're pretty damn bad there. But then with the first wave, a second wave, and a third wave, as though nobody had learned anything from the past. All right. Now let's look at the other part of the world, Japan. Now, Japan, this is amazing. I mean, this is going to look similar, but then look at the numbers there. We see a third wave, but look, I mean, they're doing an incredibly good job in absolute, well, it's about more relative numbers. I mean, this is a very small portion. This is per mil rate of the population that has been hit by the virus. Still, it's dangerous because we see the exponential growth here. If they're not careful, I mean, very easily this can explode. South Korea, it's even better. And now the best in class, I mean, I didn't look through all the countries, but I looked at those countries where, well, first of all, I only looked at those countries where the political system is reliable to give kind of good data. Now, the best in class, that's Taiwan. I mean, Taiwan, almost nothing. But these countries, especially Taiwan, they were hit by the SARS epidemic already more than a decade ago. And they didn't forget about that. And so they reacted very, very quickly and with very, I was going to say strong measures, no, with very quickly, with very efficient measures. And they didn't go into a lockdown. So it's feasible. It's just be reasonable, learn from the past, and don't get into trying to avoid a third wave. All right. Okay, so much now for the data. So let me get back here to Italy. There we are. And now let's play a little bit with our equations. So this sheet is the same thing as the sheet that we saw there before. I simplified it a little bit. And what I'm going to do is I'm going to change here three things. I start here. I have exactly the same graph as we had there before, the same equations. And what I'm going to allow is at a certain point in time, I'm going to change parameters. And I can change 1 over alpha, so the time scale for getting infected, the time scale for recovering, 1 over beta, and then also here my R is going to change also the initial R, the R at time 0. Before I do that, let me get back here to the slides. Why am I doing this? So yeah, let's never forget that. And I'm showing this here because, I mean, let me open a parenthesis. I mean, when we do reserves, our reserving colleagues, I mean, most most of us, when we're doing results, we just produce results in all impunity. I mean, we all say, of course, we do an actual versus expected, but the reality is that most of the time, if at all we do an actual versus expected, is with respect to last year, but not to our prediction of the ultimate 2, 3, 5, 10 years ago. If we would do that, I think it would be quite embarrassing. So actually, we have a tendency as actuaries of just not following this, of not just checking. I mean, does our model, does it agree with what's observed? Okay, I close the parenthesis and let you think about that. So here, the first parameter is alpha. That's the infection or contact rate, and it's kind of the number of this successful infection per unit of time. So it's the inverse time between contacts. And remember, I put it there like 5 days. So this one, it drives the kinetics of the epidemic. So how fast it spreads. And how can it be influenced? Well, we can influence it. Definitely we can influence, I mean, for example, by wearing masks. By the way, yeah, no, I can't do this now. Okay. So yeah, let's wear masks, or let's just by some behavior, we can change this, and we can change it in a quite strong way. And that's why we saw also these numbers just going down. The epidemic wasn't through yet, but we managed to reduce it simply by decreasing that number alpha, or increasing the time between contacts. Now, beta, that's the recovery rate. How you get from the infected to the removed compartment. So that's kind of an inverse duration of being contagious. And also, it also drives the kinetics of the epidemic. And this one can also be influenced, but that's more difficult. That's by medical measures. That is, for example, by finding out treatments, either with medications or with the way how doctors just treat their patients. So that is more difficult than the societal measures, but definitely also has an impact, and it can reduce this duration of being contagious. Then we already went through this. The basic reproduction number or ratio is the ratio of these two. It's kind of it's often said that's the number of secondary infections. That's how many, if you're infected, how many people will you infect? And if it's more than one, well, then you have an increase of the epidemic. And if it's less than one, if you're infected and you will overall infect less people, less than one person on average, well, then the epidemic is going to die out. That is true. This is true for this ratio, but only when all agents are susceptible. That's when S is equal to 1. So at the beginning of the epidemic. At the end of the epidemic, this is not such a good interpretation of that number, of that ratio. So be careful. That is only true at the beginning of an epidemic, when most of the people are not yet affected, have not yet been infected by the virus. And that one drives. These two were driving how fast this goes. This one drives the dynamic of the epidemic, whether it explodes or whether it dies out. Now, note this formula is very simple here for that SIR model. In other compartment models, these are combinations of different parameters. It's slightly more complicated than just this ratio here. And obviously it is influenced because the ratio of these two measures, by both societal and medical measures. There's another parameter of which I have not talked yet really about. That is the initial immunity, the number of people who are removed from the onset at time 0. So I have set this number equal to 0, but it could very well be that it's not equal to 0, simply because people are immune by nature, genetically immune, or because they have been vaccinated. And that drives the dynamics, very strongly the dynamics of the epidemic. And you will see how dramatic that can be and how useful vaccination can be, in spite of what some colleagues say. So it can be, of course, influenced by vaccination. There's another thing that you may have heard about, that's the herd immunity threshold, the HIT. It turns out that in this model, it is equal to alpha minus beta over alpha, or 1 minus 1 over R0. In the press, you often see that it's 1 minus 1 over R0, that thing here. That is true, but again, it's only true if the number of infected is much less than 1. It's in that approximation that it's true. Otherwise, it's less than that number. So that is so this R here. Mind you, with this R, I should have told you before, this R here has nothing to do with that R. I mean, that is very confusing in that model, but that's the usual lingo. So this is simply this compartment, this pool, and this is just a number here. And so this here, this R here refers to this R here. And if you're already along in the epidemic, you can achieve herd immunity already with the R, which is less than this number here. All right, so let's go back to our phenomenology. And let's play around a little bit with that. So I've tried here out several scenarios. So what I'm going to try out is here, this scenario here. I've already copied it, so I don't, or well, I can put it here. I can say see, my time here goes from 0 to 200. I'm going to say at time 44. So after 44 days, I'm going to change my parameters, and I'm going to say, well, people are now, from now on, they're going to wear masks. So if they wear masks, that doesn't affect the beta. That has something to do with medical advancements. No, this is just behavioral. And so by wearing masks, I increase the time between me and infecting somebody if I'm infected myself. So let's put it equal to 10. If I put it equal to 10, look at what happens here. So basically what it's going to do, it's going to change here my R0. This, which is 3 here, and that's pretty hefty. I mean, 3 days is quite hefty. So, and let's look here at the picture there. There we are. So you see the old picture was here. I've put it, and maybe I'll increase a little bit the size. So this was the previous one, and now that's the new one. From that moment on, you see how important this is. I've just reduced it. Let me go there. I've gone from an R0 of 3, which is up to here. I've reduced it to a R0 of 1.5. So I'm still in the epidemic mode, but see already how strong the impact is. You see now also the number of people who have been infected has reduced here by something like 25%. So it's not going to really slow down the epidemic, because you see here this dotted green line and the green line here, they merge again together there. So it's not going to stop the epidemic, but it's going to reduce a lot of suffering, because a lot of people here will not have been affected.
Frank?
Yes.
The fact that this under this scenario, it dies out well before everybody is infected. Is this herd immunity under these parameters? So is the herd immunity a factor of alpha over beta?
Well, the herd immunity definitely depends on the 2 parameters. Yes, it's really because the herd immunity depends on these 2 parameters. I mean, we saw the formula there before. So yes, it will affect the herd immunity, but I'm hesitant to give you a clear answer to your question. I don't really know. No, I don't know. I'm here at the limit of my own knowledge. It's a good question. But it definitely changes the threshold of herd immunity. It's an interesting one, yes. It should be relatively easy. Probably it's relatively easy to answer your question. But now offhand, I'm not in position to give you a good answer.
I thought I'd ask rather than think.
Pardon?
I thought I asked rather than think myself, so it's probably not too far away from the equations on the last slide.
All right. Okay. So what we can also do is, another thing is, instead of introducing the masks here at time 44, I mean, after 44 days, I mean, we've already had time here to notice that there was an epidemic. If we do it at time 33, look at the effect. I mean, the effect is dramatic. I mean, now we have about something like 35% of people who are not affected. So you reduce a lot the suffering here. So it's really worth doing that. Now, if we put on mass early, and if I change then also my 1 over alpha, if I put the 1 over alpha, I say, well, now I have really good mass, and I put it in, well, okay, forget about that. But what I'm going to do is I'm going to go back to 44, and what I'm going to do is I'm going to do a lockdown. Yeah, I'm going to do a lockdown, and by the lockdown, what I'm going to do is I'm going to increase, because people almost don't interact. So for me, the time of getting to interact with other people is going to be 60 days. It's going to take me 60 days on average to transmit the disease. So that reduces then my R0, it reduces to 0.3. And now you see the effect here. Now I really have now this exponential decrease here of the number. And you see how strong the effect is there from that moment on here, having introduced that lockdown. Reducing again the suffering by really quite a bit. Now, what I could do is I could say, all right, I have this lockdown here. I have this lockdown at after 44 days, and after 99 days, what I'm going to do, I'm just going to say, well, okay, it's good. It's good. Let's party again. Let's do that. So let me do this here after 99 days. There we are. It's pre-programmed. You have a second wave coming up. Now, one thing that we can do, we can look at this herd immunity, and remember the slide here. So yes, it depends on alpha minus beta divided by alpha. So the herd immunity only makes sense when alpha is larger than beta. And if alpha gets close to beta, you need very little people to be immune so that you have herd immunity. But if alpha is much larger, you need a lot of people to be immune. So if I take an R0 of 3, the immunity sets in with 67%, 66.6, huh? 1 minus 1 over 3. And let's do this. So let me again put here. So we start here from our initial, and what I'm going to do is I'm going to do to here at time 0. At time 0, what I'm going to do, I'm going to say that 67% of the population has been immunized, vaccinated. So we start out of the situation and you see nothing happens. It's all constant there. Now, if I would have start off with an immunity of say only 33%, well then you see, yes, then we have a peak. It's much milder than what we had before, but still we have a peak. And we see that here the difference between here those 33 and what is it, 80, 85 or so. So I mentioned it's 50% of the population still gets then has to go through the disease. So so what we can do is we can start say, well, I mean, let's be realistic and say, well, we got a vaccine, but it's only after 33 days that we start to implement that vaccine. All right, then let's put this here. We put this vaccine after 33 days. So you see here after up to there, everything is the same. And then we drop all those susceptible people who have not yet been infected. I'm going to vaccinate them. So I'm going to swap these with these here. And they're removed. They're not recovered. They're removed because they cannot, they're immune now. And so now you see here, that used to be the peak that we had, and this is the peak that we have now. It's much smaller. So you see that already with a very wide vaccination, I've vaccinated only 22% of the population, and already I have a pretty strong effect. Of course, if I now do the same thing here with those 67%, Oopla. Ah, sorry, wrong cell. Then you see that the pandemic decays off immediately. When I had that before, it still continued on, but not as strong because I hadn't vaccinated enough people to achieve herd immunity. But if I vaccinate here 67%, and the 67% comes from this 3 here, from this R0 equals 3, if I manage to vaccinate these people, then that many people, then I just kill off the pandemic. All right, and what I wanted to do is to show you this little example here and compare it to Italy. If I remember well, if I did it well, see this here and see on the data, see here how this kind of reproduces a little bit the data that we had. We had a lockdown here, and then here peak. It turns out here this peak is larger than that case. Okay, I didn't fine-tune the parameters, and then also let's not forget that maybe more people than that had been affected at the time. It was just not tested enough. Okay, so let me get back to this and finish off. And any questions up to here? Okay, so I will assume that this was all easy to follow. So we're done with this. So what are the lessons learned? Lessons learned is, if I concentrate on the SIR model, well, it's very simple, but it is extremely rich. Of course, I introduced the richness also by changing the parameters over time, but they really do. Of course, the world changed. I mean, we react to the pandemic. So if we can react to the pandemic, of course, we have to change those parameters. But already it gives you a quite rich phenomenology that is pretty good at reproducing what we observe. So they can reproduce the data. Now, one thing that we have seen a little bit, but I haven't mentioned it, is that it's very sensitive to the parameters. We saw that if you change a little bit one parameter or the other, already we had a pretty strong effect. I mean, we saw that with immunity and so on. So it's quite sensitive to the values of these parameters and the initial conditions. So it's not chaotic. It's definitely not a chaotic system, but still it's sensitive. So, and that makes it relatively difficult to calibrate. And definitely, as far as I can tell, and I might be wrong, I'm not a specialist, but as far as I can tell, I don't think we can really use it to do any forecast, at least not beyond a few days. For one reason is, first of all, the parameters change because we adapt medically and we adapt also societally, but also because it is so sensitive to the initial values and the values of the parameters. So if you get a wrong calibration, it's really the confidence intervals on your parameters are going to be quite large, and therefore you just going to get a may have a bad forecast. Now, I've talked here only about the SIR model, which is one of those compartmental models. There are other ones. I already mentioned some of those, didn't go into those details. There are also the stochastic models. I mentioned this. And one thing that is quite modern nowadays, and is probably the way of the future, is agent-based models like cellular automata. And there's a lot, apparently, I don't know anything about that, but apparently there's a vast literature on that. And lots of epidemiologists use those agent-based models, maybe in combination also with some compartmental compartments and also stochasticity. And by the way, I open a parenthesis. There was a couple of years ago, there was Astin working party on agent-based models. And this working party is going to publish its results shortly. Now, I want to say something more, but I forgot. So let me put on my Astin hat again, or my Astin badge again, and talk about the Astin Academy. And set it into context. I mean, the Astin education program, it started, of course, with the colloquia at a time when none of us was born. This is 1957. Was anybody born in 1957? All right. Okay, nobody outs her or himself. And it started with the colloquia. And the colloquia were basically at an audience of professionals with conveyors who were also professionals, either from academia or from the industry. And that has been, up to now, always the case. And there's been no year without a colloquium. Now, what we introduced a few years ago was the workshops. And this was professionals talking to beginners. And we've introduced that in parallel to those scientific sessions of our colloquia. We've introduced those workshops. These were half-day workshops on elements of pricing in general insurance, of reserving, of capital modeling and reinsurance. So this has been quite successful. We always had big attendance to that. And now we introduced, but we were stopped by Corona, introduced the master classes. And these were really authorities, people with a big name. Like for example, Greg Taylor, like Paul Emberts, like Michel Dacrogna, people who were really known throughout the world, authorities who are giving masterclasses for professionals. We are recording these in a very professional way. These are a bit like the Feynman lectures on physics. This would be, for example, the Emberts lectures on actuarial mathematics. So bear with us. We're working on this, but Corona has stopped us for a very simple reason. We couldn't get the authorities in the recording studio. Finally, the Academy, that is new thing. This is authorities, but talking to beginners. And here I get back to, I concentrate on this here, and this is going to be the next generation platform for education. This is what Jed has already done. He has already done that for this course on regression. I invite you to look at this here. You have the slides. You can download them from the chat box. You can look at this course on regression. It's a very elementary course, so it's probably too elementary for all of you. However, that is what we want to achieve. We want to talk here to beginners and do it on that template. And this time it's going to be on lost data analytics. The platform, it's going to be three things on that platform. There's going to be a traditional tutorial where people have to read. It's going to be videos with several videos with experts, and then this, what I meant here is stream, not strand. A streamed So that's a really neat thing. I mean, I was so happy when I saw that. If you go on this, you can do it yourself. You have this on that platform. You have the screen. This comes there on your browser, and you have this R code and with the window with the R code, and you can start working on that R code and make it work. I mean, really get numbers out of there, and it's. And you don't have to install anything. It's just you run the R code directly on the on that platform and not locally on your thing. So you just change a little bit the code. You change replace a 3 by a 5, run it again, and you just see the result directly. No need to install anything. It's very, very convenient. And the format is going to be free and it's going to be open to everybody. Like this template here, the course that Jed already did before on regressions. Now, why am I spending so much time on this? I'm spending so much time on this because I want to get you guys on board. I would like you guys to just have a look at the proposal of Jed and the plan to do this. It's going to take place over the next 6 months. And if you want to volunteer, please don't hesitate. Well, first, please want to volunteer, and then once you have wanted to volunteer, just do it. Just contact Jed or Miyuki with a very short CV. Don't bother them with lots of literature, and they will bring you on board as volunteers for that project, which is going to be showing the future for education, for actuarial education. All right. So that's what I wanted to tell you. Thank you all very much. And I hand over, unless anybody wants to ask a question, I will hand over to Jeff.